this device, which will sit here, is basically a very high power plasma, flamethrower.
Hi Troy, great to have you on the podcast. Thank you so much for having me here in what is an amazing facility here in Oak Ridge.
Glad to be here. Thanks for inviting me.
Much appreciated. So today I want to talk a bit about your career, a bit about some of the processes you've been involved in your career, and also hear about your work at Oak Ridge, and also dive deep into the facility we're sitting in today, which is looks like there's a lot of progress happening.
It's in progress. Yeah. It's exciting though.
Amazing. So I'm aware you started your career in the plasma physics domain and exploring a lot of areas there. Do you want to talk a bit about some of the research and academic work you did earlier in your career?
Yeah, I can give you the whole story if you want. I got interested in fusion at a pretty early age in high school. Actually, my high school chemistry teacher had us do a debate on nuclear power, and I had learned about fission. I also learned about fusion. Decided that was something that interested me, and so I took that path, and here I am now. I went to school as a nuclear engineer and physicist at NC State, Princeton for plasma physics, and then all the while interested in fusion. But when I got to Princeton, even though there was the TFTR reactor that was operating at the time, got the 10 megawatt fusion power result back in the 90s, I worked on a more fundamental plasma experiment, so studying a process called magnetic reconnection. That is the reason that solar flares happen, so energy release in the solar corona. But that same process also happens inside of fusion devices. So it had relevance to both. And as I continued my career, I continued to have that kind of two sides of my personality, studying kind of basic plasma physics that are motivated by stars, anything you look up in the night sky and it's glowing, so astrophysical plasmas. But then also working on devices like the D2D tokamak and mass upgrade and other devices like that. As I went to UCLA as a faculty member, and there studied again basic plasma physics with a big focus. So I ran a facility called the Basic Plasma Science Facility. Not very imaginative, but the device was called the Large Plasma Device. Its acronym was LAPD. So that's a little more imaginative and relevant to the Los Angeles area.
Yeah, amazing. So you've bounced across both coasts and explored some of these plasma phenomena in the interstellar realm, but also here. Some of those phenomena you mentioned, is that favorable phenomena in a fusion power plants, or is that kind of an instability that you're trying to understand using?
Yeah, well, in my career, I was really studying a lot of instabilities over the years. So reconnection, this process is it can be desirable. You can make use of it to start up, say, a tokamak plasma, for example, as a way to inject current, something called coaxial helicity injection. But mostly it's a cause of problems. So these instabilities, reconnection can cause many things in a tokamak. Some can be benign. It can be causing more transport than you like, but they also can lead to something called a disruption, where the plasma just gets angry and throws itself against the wall. So that's not good. In addition to studying that bad process, I spent a lot of my career studying turbulence that leads to leakage of heat particles and momentum out of these devices that you're trying to confine, these super hot gases, plasmas with magnetic fields.
Okay, amazing. So you're understanding these and studying these kind of turbulent and temperamental plasma phenomena has been like a really important input to the fusion energy domain that's happening at the moment. So what was a lot of the focus at your work at UCLA?
Yeah. So again, kind of two sides of the personality. I did things. So one problem that I worked on that was very fundamental astrophysics was understanding how matter accretes in collisionless black hole environment. So accretion disks around black holes, where the plasma is so hot. Usually the way that matter falls into a black hole is much like how matter falls out of orbit of the Earth. So if a satellite experiences some drag in the atmosphere, it'll lose its angular momentum and fall in. The same thing has to happen for accretion disk material to fall into a compact object like a black hole. Plasmas are interesting. So it turns out the hotter they get, the less collisions there are. So it becomes, as we say, collisionless. and you don't have these usual drag mechanisms that cause matter to lose angular momentum and fall in. And so usually in a plasma, you get processes that are associated with instabilities, with turbulence that replace collisions and cause transport to happen. In the case of the accretion disk, it's how you explain how the matter falls into it. In the case of a tokamak, it is a bad thing because it's why the heat and particles leak out. They get transported by these turbulent processes. But in the accretion disk problem, it turns out there's an instability that happens in the accretion disk that's called a magnetorotational instability. Yeah. And so I studied aspects of how that worked. Really, I studied aspects of where that energy went. As it turns out, the amount of energy released by falling into a black hole is tremendous.
Yes.
And that energy can go into this instability process, and that goes into a wave that I studied for many years called the Alfvén wave. And that wave, you can understand, I can try to explain it simply. It's like a wave on a violin string, yeah. But now the violin string is a magnetic field line. And you think about plasma being kind of attached to the magnetic field line. You pluck it and you get a wave that propagates away. So that's what we call a shear Alfvén wave. And this instability is really like that wave. And you get a lot of energy that goes into this wave, and it has to go somewhere. So I studied the process by which it goes through what we call a turbulent cascade, and you get big waves. It's much like eddies in a river. You get big eddies that make smaller eddies and smaller eddies. That's the usual turbulent cascade. You get the same kind of process with Alfvén waves, where you get waves that collide with each other, generate smaller waves, and eventually heat. It's a long-winded story. Yeah, understanding nonlinear processes associated with Alfvén waves and how that explains accretion and heating in accretion disks like the one at the center of our galaxy. And so to complement that, I worked also on confinement issues in devices like tokamaks. Yeah. So really trying to understand how to understand how turbulence makes confinement worse. Yeah. And also how to mitigate it and control it. And so we did a series of experiments trying to use the same mechanism that underpins good confinement in tokamaks. We call this high confinement mode, or H mode, where you get a transport barrier at the edge of the plasma that basically what happens is you're trying to make the temperature and density in the core of this device reach a certain level. But the problem is, as you pour in energy, you're trying to heat it, keep it hot. Heat flows out of the device faster than you like. So you have this constant filling of heat and particles and constant loss, and you reach a steady state. But if you go into this H mode, what you get is a transport barrier at the edge. It's as if you had a hole in the dam and you put your thumb in it. Yep. And so what happens is the water level will rise up behind the dam. And you get to much higher, about a factor of 2 in temperature and density. And that's a huge win for fusion power. So a lot of the devices that we're thinking about now will operate in H mode if possible, if they're tokamaks. Yeah. So understanding, how that barrier happens, and it's related to flows in the edge, have been a focus of my program at UCLA.
Interesting. Yeah. So when looking at, obviously there's a lot of natural phenomena out there that underpins fusion, and a lot of them is, astronomical related and interstellar related. Are there still a lot of questions that need to be answered about how that phenomena works to help us apply it to a fusion power plant?
No, absolutely. I think, we've made tremendous progress. So because of investment from federal governments around the world in understanding the physics of plasmas and magnetic confinement situations, we've learned a tremendous amount. Now have the ability to make predictions. This predictive capability really helped the NIF result happen. It helped the JET result happen. But there's still a lot of work to be done. So I think, to make fusion economical, we have a lot of other things to do that we'll talk about. That's really the focus of a lot of what we do at Oak Ridge. But you got to squeeze every ounce of performance, if possible, out of your plasma. So being able to get it to as high a temperature and density as possible, hold it there very well when you get good confinement, avoid and mitigate instabilities. There's a tremendous amount of work still to be done on that front that also, has, again, synergies with these space and astrophysical plasmas with plasmas for processing. There's all kinds of benefits, spin outs beyond fusion.
Yeah, amazing, amazing. So you've done a lot of fundamental science in your career. You've then started talking about some of the applied sciences using, tokamaks and looking at some of their different modes and configurations. How have you kind of now launched that more further into the application into fusion energy? So maybe I know that you were involved in some national strategic planning processes. Really interesting to hear about those.
Okay, yeah. Well, I mean, I got engaged in a lot of planning processes, both at UCLA and then, it's one of those things where I guess I have some ability to herd cats, as I like to say. And so helping to lead these kind of processes, I eventually found myself doing strategy for the U.S. fusion community through the Fusion Energy Sciences Advisory Committee. So the most recent process, I've gone through a couple of them. I won't talk about the previous ones because those weren't as successful as the one most recently. Yeah. But this one was launched back in 2018, really. And it was meant to be mimic a process that's been done in the high energy community that's been very successful. And a foundation of it, a very important part of it, is actually getting the research community to work together and come up with a set of priorities, or come up with a set of, enumerate what are the opportunities, what are the priorities, and in that way build consensus around them. Part of the problem of the fusion community and the high energy physics community before that was a lot of, I would say, not everybody's on the same page about what we needed to do as a community. And that, for whether deserved or not, resulted in a Congress and others looking at the community and seeing it as fractured. So having this first process, which we call the community planning process, where people were able to actually have their voices heard, work together and come to some consensus on what we needed to do. That was absolutely essential. And that was led by a very strong team of scientists and engineers from the community. Without that, what I did next would not have been possible. So that the PSAC committee then had a subcommittee, and the task was to lay out what are the priorities, what are the gaps that we have to address to get the fusion energy. An important outcome from that started with the CPP, started with a National Academies report that Mike Mall at Columbia led, that really called out that we were ready for a goal of trying to get to a fusion pilot plant, an electricity producing pilot plant. And the community leading up to the PSAC report said, we're ready to do this and we can do it by the 2040s. And so there was kind of an agreement among everybody that we should be targeting an energy goal and not, we've been doing science for a long time. The science has been great. We'll continue to do science because that underpins any progress that we're going to make. But let's target that energy goal. And so that report has been successful in getting attention from the government, signaling that the community is kind of behind this. There's a consensus, and importantly lays out kind of what we need to do next. And we can talk more about that. There's really 3 areas of science and technology that we need to focus on addressing to get to that fusion pilot plant goal.
Mm-hmm. So this report has been a really important input for the inflection point in that fusion's undergoing at the moment. It'd be really interesting to hear about those areas that were the findings from that planning process.
Right. I mean, I guess maybe I'll start with why do we think we're ready for energy, and then what do we have to do next? I mean, it's steady progress, that steady investment by public sector to get us that predictive capability really got us to a point where we've able to make predictions. Again, the NIF result was because of just understanding and kind of using that understanding to optimize the pellet, the laser pulse, the holorum, all these things together. And that really was built upon that progress that was from investment. The result on JET made use of a lot of advances in magnetic confinement fusion. So that was essential. You have technology breakthroughs, so we called out in the report. One thing, I mean, there's many things to call out, but the magnet progress that was made at MIT and CFS, and then the private sector starting to pay attention. So all these things. So I would say the report had a big role, but probably there was a confluence of many things. I mean, I think the private sector really drove a lot of the attention and the progress that we made. But again, it wouldn't have happened without that investment and the public sector's progress over many decades. what's next? So what do we have to do? So this report identified, if we want to get to this fusion pilot plant goal, there's really 3 areas that we need to focus on. And 2 of the areas have had less attention than the first. So the first one is sustaining a burning plasma. So, how do you take this? You're trying to recreate what a star does, right? So you're trying to hold some way you need to confine very hot plasma with enough density, enough temperature for enough time so that fusion can occur. So, there's a lot to that. There's all these instabilities that I mentioned. There is a lot of progress there. So as far as these 3 categories, that's the one where the most investment is made, the most progress has been made. And honestly, that's what, that progress is what enables the private sector or makes them see the opportunity. We're poised to be successful. There's still work to be done. So that still is a gap, and we enumerated a lot of areas of work. The other 2 are really have to do with what's around that plasma and how do you harness the energy that it creates. And so this plasma has to be within some physical vessel.
Yeah.
And that physical vessel is in an extreme environment. So you have in a case of a magnetic confinement device, you've got, 500 million degree plasma right here, and right over here, it's, maybe not room temperature, but close to it.
Yeah.
And so you've got, that 500 million degree or 100 million degree plasma.
Yeah.
There's going to be a lot of heat flux and particle flux coming out of it that impinges on the material. And in fact, this device that's sitting right here is meant to help solve that problem. On top of that, the reaction that we are likely to use, certainly first, the deuterium-tritium reaction, that reaction generates a neutron. And that neutron just goes flying out and into the material surrounding it. And that neutron can cause a lot of damage to the material. So you have to find materials that can withstand that tremendous heat flux, that tremendous neutron flux, and be, last long enough. So this can be economical, right? You don't want to replace your wall every month. You have to have materials that are some kind of way to operate economically, and materials are key to that. The third category is really, we call it harnessing the fusion power. So it's there's a couple elements to that. You need to capture the energy. So most of the energy in the DT reaction is in that neutron that goes flying out. And so you have to capture that neutron and, do something with it, usually a steam cycle. Maybe you do it without steam, you do it with some other working fluid, but it's a standard kind of approach where you spin a turbine and most ideas about how to do this. But then more importantly in that, you have to generate the fuel. So the deuterium is abundant in seawater, in tap water, you pour it out, you got plenty of deuterium, heavy hydrogen. Tritium you have to manufacture.
Yep.
And so the task is to pretty much every neutron that comes out of that plasma, that reaction, you got to capture it and use it to generate tritium. And so you put lithium around the plasma and you try to squeeze every neutron you can out of that plasma and capture it and make it into tritium, because otherwise you don't have enough fuel to keep the reaction going. So that's it. Both of those, the materials challenge, the fuel breeding, and the harnessing the energy. Those are areas where we've had less investment, and those are the significant number of gaps there that we have to address if we want to get fusion on the grid. In that report, we talked about the 2040s. The private sector are more aggressive, as is the National Academy report that came out around the same time that said if you want to have impact by mid-century on energy sources that are carbon neutral, you have to really have things going in mid-2030s. And so that timeline, you have to be aggressive. It also called out, and our report did, about the need for private-public partnerships. I mean, the U.S. vision, what we're trying to do in the U.S. is commercialize fusion energy. That's the goal. So you need industry. That industry has been seeded by tremendous investment right now. The U.S. fusion strategy is that we work with the private sector to realize this fusion pilot plant. But the public sector plays a key role. I mean, all those gaps aren't going to be closed by a company. It's going to be closed with everybody working together. So it has to be public sector pushing forward the foundational R&D, helping to translate that towards the private sector, and then working with the private sector to enable their aggressive timelines.
Mm-hmm. Yeah, that makes a lot of sense. And I think it's a very elegant way of outlining some of those key focus areas and gaps that need to be closed. So you mentioned about basically the public and private roles are evolving, because in recent years there's been this insurgence of investment and activity from the private sector. And you spoke about doing research and helping to translate that ultimately to be commercialized and taken forward by industry. How do you see the role of a national laboratory? It might be great to talk a little bit about your role that you have at Oak Ridge.
Oh yeah, yeah.
And,
all right, and
how that fits in.
Right. So yeah, I made the move to Oak Ridge just 9 months ago to be the director of the Fusion Energy Division here. Again, I mean, I talked about this report and laid out what needed to be done. I mean, Oak Ridge is a place that has capabilities across all those areas. That has the core plasma physics, but also has capability. It's a materials lab. Oak Ridge was built as part of the Manhattan Project, or has its roots there, and really has materials at its core. But the technology too, the breeding technology to make tritium, the expertise is here for that. So that's that's one reason I'm here. Now, in terms of the role of the lab, it's been landscape of fusion has changed pretty dramatically. You go back, certainly when I started my career, I won't say how long ago, but it's been a while. The public sector was where the activity was. It was, a long-term activity. At the time that I joined the field is when really the program had a shift from an energy focus that started in the 70s to more, we're going to do science and we're going to lay the groundwork for an eventual energy push. But in the last 5 to 10 years, of course, I mentioned the report and called out the need to really, we need an energy goal. And then the private sector involvement. So it's a change in the landscape, a change in the role, but I would say it's not a fundamental change in the role of the public sector. Public sector at its heart is pushing for foundational R&D, and with an eye towards translation. So making that R&D getting it to the level where you can push it out to market is a core value, role for the national labs and the universities. It's now just finding our feet in working with the private sector is not something that we've done in the fusion space until the last 5 to 10 years. And so that is, I think we're working through that and we're finding ways to partner. We need new ways and faster ways to partner because there's a timeline mismatch. But I'll also say that it's important to note that while as we look to create a fusion industry, there has to be a role for the national labs and universities to work with the private sector, help them solve their problems. But at the same time, we have to have the long view at the national lab. So we want to make sure fusion is economical and in the US and a successful industry. And you have to keep pushing the boundaries and doing foundational R&D that may or may not align with immediate needs of the companies, but it may be what they need in 5 years, in 10 years. And it may be that the company you need that makes that widget that's going to make it successful hasn't been spun out yet. Yeah. And that's the role of continuing foundational R&D at the labs, at the universities. Yeah.
Mm-hmm. Yeah, I've seen like a lot of, when they show TRL scales, they show, a lot of foundational science being done in, universities and other research institutions, and then national laboratories are really that handshake between, getting between that early foundational piece through to a commercialized, revenue generating piece of infrastructure. And so Oak Ridge has a lot of success with that from the fission sector, and also just a lot of their other science activities that are undertaken here. What's the portfolio of fusion look like, and how is it thinking about this industrialization of its science?
Yeah, right. I mean, the portfolio here, I think, again, the strength of Oak Ridge is just the capabilities across almost all the areas that you need for fusion. So doing the work on developing and qualifying materials, finding innovative ways to develop technology to breed fuel, and a lot of enabling technology. So the group at Oak Ridge has been heavily involved in technologies that have been used to enable us to get to fusion temperatures in plasmas, heating tools, magnets, and fuel injection, right? So pellets is a big role of Oak Ridge that have just being able to fuel this plasma. It's very dense plasma. You have to inject cryogenic fuel into it and developing that technology. And that's actually a case where that technology is getting to the maturity where you might want to look to transfer it out. And that's something that we're actively thinking about. There's still R&D to do there. We haven't done it with tritium, and that's a challenge because it's radioactive. It heats itself.
Yeah.
And there's other challenges that we can go into. But, we certainly have an eye towards translating that. We're working with Tech Transfer Office. There are, fusion startups that are interested in that technology and licensing it. And so that's a new stance for us in the fusion space. But it's one that we're, again, the lab, as you said, has that experience. And certainly the leadership of Oak Ridge is very on board with looking towards or having tech transfer. We're an Office of Science lab. We do science, but we keep in mind, we keep tech transfer in mind as we do that.
Yeah, amazing. So you mentioned, Oak Ridge really has its finger in a lot of different aspects associated with making fusion happen. In your portfolio, do you want to talk about some of those areas in a little bit more detail?
Sure, I can give some examples. I guess, maybe, again, we have expertise across all these three areas. Thinking about the plasma physics, we have a great strength in understanding how magnetized plasmas behave. One example I'll give that intersects the private sector also is we have a great expertise in modeling and understanding the boundary region, the exhaust. And this is a big challenge. So one of the gaps that we called out in the report has to do with having a high performance, so a high density, high pressure, high temperature core plasma where fusion is happening, but you have to have it exhaust the ash because you're going to make helium, you got to get it out. So you have to have some flow of particles out. That's going to carry heat out too. So having a solution where you can bring that heat out and not, try not to destroy all the materials around you, right? So come up with some solution for that also is compatible with that high performance core. That's a key gap. And this is where expertise at Oak Ridge is playing a role. So to mention the specific example, we have been working with Commonwealth Fusion Systems to develop an exhaust solution for their Spark device. Yeah. So coming up with a way, doing the modeling in the edge where what you would like to have happen is all that energy doesn't come out and just impinge on a very small area of material, because that's what can happen with a diverter. What you'd like to have happen is a lot of that energy gets radiated away before it gets down to the material. Yep. And so-called detached diverter. And so this modeling that we did with CFS, yep. Was targeted at finding solutions with modeling neutrals, the edge plasma, where you get this detachment routinely. So that's one example. Maybe another example in the plasma space, but then connects to the technology. So, the fact that Oak Ridge has capabilities across all these areas is important if you want to be able to do integration. You want to think about effects that, go from the plasma to the blanket and to the materials, right? So having that integrated view of the system is a strength of Oak Ridge. And so another example of a project where integrated modeling is being developed, a project called Frida or Frida, I don't know how she pronounces it, that Kami Collins leads, is looking to do integrated modeling, including plasma simulation in the blanket, for example. I mentioned earlier in the conversation about this disruption where the plasma throws itself against the wall. Yeah. So that, your blanket may have liquid metal in it, right? Yeah. So that's at least one option. There are many options. And that liquid metal, there's going to be electromagnetic interactions between the plasma and the liquid metal during that kind of event. So having the capability to simulate what that interaction looks like, that's something Matt Beidler has been doing at Oak Ridge, along with others. That's an example of using that integrated capability. Materials is always a core strength. So we have a long history of fusion materials, developing materials for structural components as well as plasma-facing components at Oak Ridge. On the breeding side, we have a lot of activity on modeling now, but we're looking to expand that to experimental facilities, looking at molten metal, so liquid metal, molten salt. That's where I was going with molten, and other technologies that can be used for breeding. Yeah,
amazing. So in the materials domain, so we're sitting right now in the MPEX facilities.
Right.
You can hear that we're in a working industrial facility because we have valves going off and ventilation. And we're also in
we're wearing safety glasses.
We're wearing safety glasses, and you can probably tell it's a warm day here in Tennessee because my goggles are fogging over every few minutes.
Yep.
But it's great to be here. And so can you talk a bit about what the purpose of this facility is and where it's at?
Yeah, absolutely. So MPEX, or the Materials Plasma Exposure Experiment, is really targeted at finding solutions and understanding the science and technology associated with plasma material interaction. So again, this this exhaust, that's kind of like I keep saying like a space shuttle booster rocket, but I should say a SpaceX engine, just blasting the material continuously. You expect the material to erode, to be damaged by this, and trying to understand how that works, how the plasma, erodes the material, how you get feedback to the plasma from that, because that's an important topic too. This device, which will sit here, is basically a very high power plasma, flamethrower, I guess you could think about. So the idea is you generate a plasma at that end. You put a couple hundred kilowatts of RF waves that come from over there into that to actually generate the plasma. That flows downstream, and then you inject even more RF. So you inject waves that will heat up the electrons, heat up the ions, so you can tailor the plasma that you want to simulate. That's maybe like what's in a stellarate or what's in a tokamak coming to a diverter. And then you channel that down the magnetic field. There'll be strong electromagnetic superconducting magnets that hopefully will be delivered soon. The first ones are coming later this year and in the summer. And there'll be a target here where you'll have a material or a small component that you want to test and just blast it. And the capabilities here are so that in 2 weeks of continuous operation, this will operate continuously. You get the equivalent of 2 years of exposure in a fusion device. So you can rapidly test to end of life materials and see how they behave. It will also have the capability of handling irradiated materials. And so the idea is, as I mentioned, so the neutrons will damage the material. There's all kinds of mechanisms for the damage. You can think about the neutrons flying through and just bumping through like it's, a billiard ball going through the lattice, and it just the atoms get sent every which way. So the material kind of gets scrambled. At the energy of these neutrons, you actually get a lot of nuclear reactions. A key one is an alpha or helium-producing reaction, where it runs into a nucleus and spits out a helium, and that helium can accumulate. You get bubbles in your material that make it anyway. So all that damage from the neutrons can enhance or be synergistic with the plasma damage. And so doing those together and understanding how the irradiated material behaves in the exposure is also a key focus here.
Okay, amazing. And this is one of the first of a kind capabilities globally to be able to do some of this.
This will be world leading. There are capabilities that have been used to push forward the science of PMI. The Pisces device at UC San Diego, we collaborate with them. There's devices in Germany at Jülich that have also been but this one will have capabilities that will go beyond those, and again enable this capability of end-of-life testing in a short period with irradiated materials, with relevant parameters to the edge region of the devices that we need to understand this behavior in. There we go.
So a lot of great analysis and science and will come from this. On the fusion power plant side, what are the specific questions that are going to be answered by something like this?
Right. So in part, it's identifying materials that you want to put in those environments that are going to be robust, that can survive, but you're also answering questions of how the material erodes and then can be redeposited. So all these kind of fundamental plasma material interaction processes. There's questions about, there's magnetic fields, of course, and the angle at which these magnetic fields come into the target. That there's science there that you want to understand and how that impacts the erosion characteristics and redeposition. And so you'll hope to learn from that basic science, but also use that to build plasma components, right? So plasma-facing components that are not just materials, but you got to worry about the materials and how you connect them to cooling, apparatus below, and how you engineer these things and build them. And so MPEX will be a piece of that. There's other capabilities at Oak Ridge that will be brought to bear on advanced manufacturing of these materials. Once MPEX materials have been exposed, you're also going to want to characterize them. Behind us here, we have a space where you can do electron microscopy. We also have facilities on campus that can look with other techniques at the damage and understand it. And again, use that knowledge to try to develop better materials, develop better components for fusion devices.
Okay, amazing. Yeah, I think that when we're looking at the fusion plants moving forward, can companies, engage with the national lab to be able to use this facility?
Like,
how is it looking to operate?
Yeah, right. So we're developing that plan now, but a key principle of it is we do want to be able to have private sector users here. And so we'll develop that model. Back when I was at UCLA, I ran a user facility there, and we did have external proprietary users, and there's examples of how to do that. The D3D device has become proficient at doing this now and has a lot of private sector users. So we're looking to build on those models, but absolutely, our goal again is to work and enable the private sector to do what they need to do. Part of this facility's time will be dedicated to that.
Okay, amazing. And when is it due to be up and running?
So it always depends on when everything comes in, but they're hoping to have it completed and operating in 2027. We'll be building the team and the operations plan in the near term. In the meantime, right? So we have to start commissioning. As you can see, it's coming together. Things are going to be changing rapidly. The vacuum vessels that have come in, and so as they start to get components, it's going to build up. But we want to start engaging with the research community on a near-term plan. So we're going to have a workshop next spring where we're hoping to invite a lot of people in to help us define collaboratively what we should be doing with the early research plan here, and that will involve the private sector.
Amazing. Well, it sounds like it's going to be a very hot demand facility and probably oversubscribed. But
yes. But yeah, we're gonna try to get we'll get great science out of it. We'll get great understanding and hopefully enable the development of new materials and again, success for the private sector in their endeavors.
Amazing. So I'm also aware that Oak Ridge has a connection to the ITER program.
Yes.
So it's, if I'm correct, it hosts the office, the US ITER office.
That's right.
How does that all operate and what are some of the activities happening there?
Right. So the ITER project is run by Kathy McCarthy. So they run the US ITER project, and so all the ITER funds that are mostly going towards fabricating, procuring items for ITER construction runs through that office, and they, all kinds of things are procured here. I mean, one big one that they successfully did with General Atomics was the central solenoid. But our division works with the ITER project to do R&D needed to lead up to define what those components should be, to help them with their procurement process. So we have ITER work in this building. So just over there, we have a what we call a resonant ring that is meant to test RF components. So ITER ICRH, so ion cyclotron resonant heating waveguides are sitting over there, ready to be tested in that ring. The idea is we want to not have these very high voltage, high current components break down. And so that's what this testing is about. We're also developing diagnostics for ITER, and so doing R&D on those diagnostics in concert with the project. Yeah.
Okay. Amazing. So obviously, there's been the injection of a lot of private industry in the fusion space. How does ITER still stand as a really important input to the R&D to help private industry as well?
Absolutely, yeah. In fact, there's many things to talk about there. One thing that's clear as a result in the near term is that ITER is building this device at scale. So it's the first attempt to build a fusion device at power plant scale. And so the lessons learned from designing it, procuring, developing the supply chains, assembling it. These are huge, important lessons learned. And so the private sector is very, very interested in getting access to that information. And in fact, one thing that we do here at Oak Ridge is help with that information sharing. So somebody in my division helps manage that. And the private sector is very keen on that. In fact, there's a workshop at the end of this month that's a private-public workshop at ITER to bring private sector in to talk about how that information sharing, what else can be done in that space. So there's a lot of interest there. ITER, ITER is still very important in concert or in parallel with what the private sector is doing. So ITER will be a device that provides a burning plasma, not for power generation. It's focused on the science, providing an instrument that can, long pulse length burning plasma that's very well diagnosed. So this is going to be essential to understanding the burning plasma physics that will enable private sector, even if they're trying their first of a kind fusion pilot plant on a time scale where ITER can't contribute. Getting information from ITER is still going to be essential to make that economical going forward. So, second of a kind, nth of a kind, really developing the burning plasma physics we need to understand to make fusion economical. ITER provides a platform for that.
And will the findings from ITER only be relevant to toroidal concepts, or is there physics and R&D that'll be beneficial to potentially other configurations?
Yeah, I mean, obviously as a tokamak, it's going to directly benefit tokamaks, right? Yes. But things like stellarators, there's going to be a lot of information gained. But even devices like mirror machines, Z-pinches, there is some fundamental physics that's going to be learned. I mean, really understanding how a burning plasma behaves. We've never been in, we do have this state now with NIF, but looking at a well-diagnosed, sustained burning plasma, there's a lot of science questions to ask there. And these will have benefits across the board for magnetic confinement devices.
Yeah, amazing. So to go bring it up a level, what excites you the most about fusion energy at the moment?
Yeah. Oh, there's all kinds. I mean, I think it's exciting times. I think looking at all the opportunities. I mean, again, this is why I came to Oak Ridge. I mean, just all the things that are done here, the experts that are here. My job is to enable them to be successful. And I get to live vicariously through them as they do their science. I mean, I love coming into the lab. I'm an experimentalist. But I'm excited about the opportunities. I'm a plasma physicist at heart, so I think there's a lot of fun stuff to be done there. But really trying to solve some of these technology problems. I mean, this machine's going to be a lot of fun. I'm hoping to play on it if they let me turn the knobs. I shouldn't say play on it. I hope to contribute to the science program.
Sounds good.
But that's going to be very exciting. And I'm really looking forward to building up a strong team that will do that PMI science. And that's not just here. I mean, we have to have a core team here. But I want to bring in our university partners, or other national labs, of course, the private sector to help drive that. That's going to be very exciting. And then the technology side, we have we have a great blanket team here. We need to get them building hardware and really testing solutions experimentally. They have excellent computational capabilities. But I'm looking forward to growing that hardware. There's some pieces of it over there, some helium cooling loops that are relevant to both plasma-facing component technology as well as blanket technology. Building more of that up is really something I'm really excited about.
Amazing. Well, it sounds like a very exciting time, and I appreciate you sharing insights about your career journey, about your time here at Oak Ridge and some of your work, and also getting the opportunity to have such an intimate background with MPEX and seeing it come online. So thank you, Troy.
Glad to do it. It's been fun. Sorry for all the noise, but like you said, people are actively working.
Yeah, that's good to see, and it's and I think it's the authentic experience of kind of living and breathing it. So thanks again.
Okay.
All right, discussion.
Thank you.